Hello, people. Let's talk about, let's begin with the nice way to analogize a couple of kinds of scenarios, and that is how we can talk about sources of and expressions for, well, different kinds of fields, electric fields and magnetic fields. Well, and uh, let's assume the existence of a positive charge Q, all right, and let's say that there is a point P at which we want to analyze or evaluate the presence and or strength of a field. All right. Well, what we know is, Coulomb's law and or Gauss's law can allow us to generate an expression for the electric field at that point. Um, and what we end up with is that the strength of the electric field E goes as K Q over R squared. Sometimes we like to write that in terms of the permittivity of free space and Q over R squared. Okay. Now, a couple of things here. One is that that's the magnitude of the field where R is distance from Q to the charge to point P. If you want to write this as a vector equation, well, the best thing to do here is to add that this points in what we call the R hat direction, right? And that means that there's an electric field E right there, and there is a vector R that looks like this. It is a position vector. It locates point P relative to our charge, right? And therefore, that also defines for us the R hat direction, because the R hat is a unit vector in the direction of vector R. All right, so that's sort of that. Now, the magnetic field at this location, well, as of the way we have this thing drawn, there isn't one. All right, there is no magnetic field at that location at point P, unless we say that this charge is moving at a speed v, or at that velocity v. All right, and now because we have motion of charge, now we do generate a magnetic field at that location. And what's pretty neat is that the magnetic field, the expression for it follows much the same form that the electric field's expression does, except we go like this. Now, why is this mu naught? Mu naught's called the mu naught is the permeability of free space. The magnetic permeability of free space. Epsilon naught is the electric permittivity of free space. I sure wish I had written vacuum permeability and vacuum permittivity. Those are about the ease with which fields exist in, well, in this case, a vacuum, or are created in a vacuum. And different substances, as you know, like we have dielectrics with electric permittivities equal to kappa times epsilon naught, or that's the dielectric constant. Okay, fine. I digress. Now, what I left off with here is, why is mu naught in the denominator instead of the or it's in the numerator instead of the denominator? I can't really comment on that. But what I can say is this: we still do get an R squared dependence for magnetic field. All right, but a couple of things matter. All right, here for electric field, all that matters is, well, that charge, the magnitude of that charge. Here what matters are two things: the magnitude of the charge and how fast the charge is moving. And so we can start with that, QV. All right, and let's see. Well, that's really kind of it, to tell you the truth, for the magnitude of this field. all right? However, as you probably, maybe you know, what we would do for to find the direction of this field is I would say that, well, this is almost like a part of a current going in this direction. And so I would put my thumb along this directional line and wrap my right thumb, and then wrap my fingers into the board here, and we get a magnetic field here that goes into the page. There's B. All right. Now, so if we want to do this, how do we get that B into the page? Well, what we have to do is we have to employ a cross product. All right. That's how magnetic fields work. They are in a direction that's perpendicular, in this case, to V, and also perpendicular to vector R. All right. And the way that we do that is we actually want to kind of stop here in terms of magnitude. We don't want to add anything more to magnitude, but what we do want to say is that we want to employ the fact that it's perpendicular to vector R. But what we can do is just add a cross product with the R hat vector. And then that's it. And then we're there. Okay? So the nice thing about performing this cross product is that it's really only, I mean, the magnitude of that R hat vector is just 1. All right? So all we're really doing there is saying this allows us, or really requires us to say that if there's going to be a magnetic field at that location, there must be this relationship between R, where if we say basically V cross R hat is magnitude of V times magnitude of R hat times the sine of the angle between them. Well, magnitude of R hat is just 1, so this is really, the magnitude of this is just V sine theta. So we look at this angle here. Here's the R hat direction. Here's an angle theta. And as long as that angle isn't 0 or 180, then there is a value of sine theta. All right, so as long as what we're really saying is, as long as there's some component of V that's perpendicular to the R hat direction, then there is a magnetic field at that location. Okay? Okay. Now, what I want to do is grab this. I'll make some modifications to it in a minute. Let me copy and go here. And let's transition from looking at a single point charge to part of a current. All right, and what I mean by that is, let me just sort of get rid of the, I don't have to get rid of much of this, except I'm going to change this stuff. Watch this. I'm going to group. I'm going to shrinky-dink that. I'm going to clone. And I'll say, what if this is not a single charge moving at a speed v, but what we have actually, get rid of this and this. I'm going to keep that vector, and I'm going to say that what if this is, you know, a wire that's carrying a current that at that location happens to be in that direction. All right, or really, there's some little. My direction isn't perfect. Let's see if I can. I like that better. Good. There's a little part of the current right there. Move this stuff. Yeah, fine. You get what I'm trying to. Yeah, sure. You get what I'm doing, right? Well, here's what happens. In our first case here, we started with this QV, right? When there was literally a single charge moving at speed v. Now we're saying that there is a current I that's moving along this charge carrying tube full of charges, you know, tube full of charge, yeah, you get it, a current. And what we say is, well, let's see, V we can write as, well, I'm going to write like this, dl dt, all right? there's a little tiny from here to here dl. dl just means we're moving in whatever direction we want. Okay, and well, in this case, how much charge is in our little dl? That's actually a dq. So it's most appropriate to say that there's a dq in there, right? And then we say, well, dq dt, the rate of change of current, the rate of motion of current is really, the rate of motion of charge is really I. So what we get is that QV for a single charge moving at speed v turns into what we call, turns into the term IDL. In IDL, we give the special name of, that's a current element. All right. Now, at this location, from that, from this, from our little current here, at that spot, our field looks like that, except, there's another little deal, little current element there. So this is actually, this vector right here is now a vector that I'll call IDL. All right? And this field right here is the field made by this little charge element, current element, excuse me. So it's actually one of the many infinite number of little tiny fields made by all the little tiny current elements in that wire. All right, so now what we say is, remember, we said that B from a single charge was mu naught over 4 pi, let's see, QV cross R hat over R squared. Well, now we say that for this current element, each current element makes a little tiny elemental D magnetic field, and that goes as mu naught I over 4 pi. Our QV terms, oops, I shouldn't have put that I there, mu naught I over 4 pi. Our QV turns into IDL. We keep R cross R hat over R squared. And this is referred to as Biot-Savart's law. All right? It's not too elegant, is it? I mean, yay, great, okay. But that's it. All right? That says that, a current that is made up of lots of little tiny current elements, each of them a certain distance from a point in space. Well, each of them makes a little tiny, contributes a little tiny element to the overall field at that location. And guess what? If you want to find the net field at any place, you're going to have to add up all of the little elemental contributions to that field. All right, so let's try to use this in a couple of scenarios. And why isn't there, sure, shouldn't there be, why wouldn't there be? So here, let's have a loop of current, right? And we're going to say that, how about we say current's coming down the front, up the back, which is to say that here the current is coming towards us, here the current's going away from us. And so we want to talk about current literally at that, magnetic field at the center of this loop. All right. Well, every single IDL, like here's one, I'm trying to represent that this is coming down and towards us, not down and to the left, but you're supposed to see the three-dimensional nature of this vector. coming down and toward you. All right, and if we look at that and use our right hand and put our, you can't see my thumb, but if we put our thumb, our right thumb, oh boy, in that direction, the direction of this IDL, and we wrap our fingers, our right fingers, around the wire, well, inside the hoop, our fingers point this way. No matter where we go, every single current element in this loop, the little one that's right here at the very bottom, right here, that points into the page, we put our thumb into the page. We wrap our fingers around our thumb to describe, using the right hand rule, the direction of the magnetic field, and that dB also points this way. So if we want the net magnetic field, we've got to add up all the little dBs, and that says we've got to add up all the mu naught, whoops, I'm used to writing mu naught I, mu naught over 4 pi IDL cross r hat over r squared. All right, now what I haven't said is let's define the radius of this hoop to be r. And, check it out. What's, and this, we said the hoop carries current I. Well, there aren't a whole lot of things that are variable here, right? So really, we can say the mu naught and the I and the 4 pi and the r squared is r. Those are all constants, right? And then what we end up integrating is dl cross r hat. Well, let's take, what's the deal with dl and r hat? Well, the r hats are in the direction, so this is from IDL to point of interest, the place where we want to know what the field is, right? And all of our hat vectors are towards the center. Let's take right here. Let's take, that's the r hat direction towards the center. And in this case, IDL points into the page. And every one of our DLs and r hats, every one of those DL vectors is perpendicular to every r hat vector. All right, so really what we're saying is these are all, I'll just sidebar here, DL cross r hat is magnitude of DL times magnitude of r hat times the sine of angle between DL and r hat. And these are all 90 degrees. So that's 1. The magnitude of r hat is 1. So our vector dl cross r hat just yields dl. So this allows us to change this, from a vector equation to the magnitude of B integrate DL. Add up all the lengths of the little tiny sections of that hoop, and guess what you get? You get the length of the whole length of the hoop, and some of us refer to that as the circumference. So we get that the magnitude of B is mu naught I 4 pi r squared 2 pi r. And the magnitude of B is mu naught I over 2 r. We can make it a vector equation again by employing what we know about the right-hand rule. Okay? I mean, really, I think this should probably, maybe not. To the right, I don't know. I'm going to leave that as it is, and just say we'll make it a vector expression again at the end by just saying the direction that we know the field is. Fair enough? Okay. Another application. Let's look at for the same hoop. Let's look at the magnetic field at point P now that is located at distance Z from the, I don't know, from the plane of the, yeah, the plane of the hoop. Sure. It's still a radius R. All right, let's take, for example, our current element IDL here. It's actually coming out of the page. And there's a vector R that goes from here to there. And at point P, right-hand rule says from this current element, let's see, I'm going to say this is light current coming out of the page, so I'm going to put my right thumb out of the page. You can't see me doing it. And my right fingers wrap this way around to yield that the dB from that element points like this. Okay? What I like to do here is look at, sort of the symmetry case and say, well, what about the one opposite that? What about the current element in the opposite orientation, or, reflected over our z-axis here? Well, that one, the current element is into the page, so my right thumb goes into the page, my right fingers curl around this way, and we get that there's a dB from that one that points this away. It's in the yes, it looks like that. There's absolutely no rule that it's supposed to be parallel or perpendicular to vector R. You get that? It's just literally like circle. Here's that current element down here. Our point P happened to be, right here, so it's tangent to that circle. Okay, and what you notice is symmetry says that, well, each of these has a component, each of these dBs has a component this way that are equal and opposite. Each of these has a component this way that add up. All right, these are each dBz's. All right, so really when we want to look at the net field, we've got to add up all the dBz's. Okay? And if we define an angle here to be theta, well, then here's 90 minus theta. And well, here's theta again. And dBz would be the opposite side, would be opposite that angle. So that means that we're adding up all the dB sine thetas. Well, what's each dB? Well, I'm going to do this. Each dB okay, each dB is mu naught over 4 pi I dl cross r hat over r squared, right? So each of our dBz's is all that junk. That's an r times the sine theta. All right, all of our dl vectors and r vectors are still perpendicular. if we look at a straight, you know, top view, like from here, here's an eyeball looking down. What's the difference really? But you know, there's the hoop, right? Here's our here's our point here's our point Z. Okay, so I'm just taking the three-dimensional aspect of this out. You know, an IDL might look like this, um, and an R vector doesn't look perpendicular there. Well, it turns out this representation, this two-dimensional representation, doesn't do us a service because it makes it look like R and IDL are at an angle from each other, and they're not. They're still perpendicular. And the, the best advice I can give you there is pick up a hula hoop or a bicycle wheel because you have a lot of those hanging around. And when you do that, you can just sort of look at any little tiny length of the wheel and then imagine the axis from the center of the hoop, and they are perpendicular to each other. All right, so I'll just let that lie. Okay, now, so that means we can turn this really just our DL cross R hat is just going to yield DL. All right. Now, the R and the sine theta, I mean, both of those things are constant. All right, so we get dBz mu naught over 4 pi. I'm going to do this I over R squared. How about this? I'll just write the DL. R squared, well, is R squared plus Z squared. So says Pythagorean theorem. Agreed? And then sine theta is R, big R, over, well, little r. So that's, oh boy, that's IDL times R over, I mean, R is another one, is the square root of that, okay? So we've got one factor times another square root, times another factor to the 1/2. So what we get here is R squared plus Z squared to the 3/2. And again, there's really nothing that varies in here. All we have to end up integrating is the DL, because the total B is the integral of all the dBz's. So it's, this is growing tiresome. Let's see, I R over R squared plus Z squared to the 3/2 integral DL. Ungroup. No, do it. Copy. Paste. So B equals, come on, yes, equals that stuff times integral of DL, 2 pi R. I gotta write it again. The pi's go. You know, we end up with a 2 there, and then we're almost there. So we get mu naught I R squared over 2 R squared plus Z squared to the 3/2. And, well, for us, I sort of didn't explicitly say this is our z-axis, but I did call that z, so you can get that's the positive z. So I say in the z-hat direction. What do you think? And guess what? We can do things like, say, here is somehow part of a, well, it's a big long wire, but we're going to say, let's look at the field here made by this section of the wire, all right? And then we're going to start to have things that do vary, you know, something from here to there, you know, maybe we vary something from negative something to positive something, or maybe we vary an angle from negative something to positive something to look at the total field there. All right, so that's next steps, but we have an introduction now to what's called Biot-Savart's law. All right, we have a way to analogize, which I'm a big fan of doing. Anyone who knows me, love my analogies. We have a way to analogize fields made by, electric fields made by charges, whether they're moving or not, and magnetic fields made by charges that we require them to move. Okay? We look at each individual for not just a single charge, but a current carrier. We look at individual sections of that current. We identify what we call the current element, right? And we can write Biot-Savart's law, allowing us to look at each little contribution to the total magnetic field at a location by each little, you know, the presence and location of each current element. All right, we can employ symmetry in some nice cases, whether they be, you know, somewhat simple or a little more complicated, or later on even a little more complicated. Okay? Okay, folks, thank you.